Okay, I want to go ahead and introduce this wonderful, wonderful model on how to solve stoichiometry problems. You see, it allows you to convert from some amount of given thing, either a reactant or product, into something that you want, either a reactant or product. How much product, say, do you form if you use a certain amount of reactant which reacts completely? And so using that, you're able to convert between all these things, either from representative particles, i.e. Atoms, molecules, or ions, or from mass, like in grams, or from volume, like in liters at standard temperature and pressure, into those amounts of those products or reactant, whatever that is that you want. Okay? It all goes through the happy place. The place where you want to go. If you don't know what to do, the place you want to go, your happy place, is the land of the mole. Yeah, you want to figure out how many moles of whatever it is that you're dealing with, and however many moles of that other thing that you're interested in will be formed. Convert into moles almost all the time, and then with moles you can convert from one type of compound into another. You can go from type of compound into another one using the mole-mole ratio. If you convert between two different types of compounds, you have to use the mole-mole ratio here. Okay? So considering all that, let's go ahead and try out this problem. The question is given. If you have 3.01 times 10 to the 23 molecules of H2O produced, find the number of grams of O2 that were needed in the combustion of hydrogen reaction to form that much H2O. Okay, so in order to do this, you need to have a balanced chemical equation. Before you ever consider using this chart, particularly the mole-mole ratio, you have to have a balanced chemical equation. So reacting hydrogen and oxygen together, you form water. So you need a balance. Let's see, you can balance hydrogen. Well, you have the same number of hydrogens on each side. How about oxygen? Well, I have 2 on the left and 1 on the right. And so we'll put a 2 over here, so we have now 2 oxygens on the right and left. However, now we have 4 hydrogens on the right. We'll put a 2 right here, okay? So this is our balanced chemical equation from which we can do our conversions. So let's see, you want to go from the number of representative particles. That's the number that you're given. Ultimately, you want to do that into moles of H2O, and then into moles of, let's see, O2, and then into grams of O2. Okay, so let's see, we are going to be forming 3.01 times 10 to the 23 representative particles, so the number of molecules of H2O. And we want to convert then into moles from the molecules. Okay, so to do that, let's see, in 1 mole you'll recall that there are 6.02 times 10 to the 23 molecules. So that allows you to go from molecules into moles of water, and then you can go from moles of H2O into moles of O2. So to do that, to go from moles of one thing into moles of another, that balanced chemical equation has a certain number of, or certain coefficients in front of each thing. You see, 2 moles of H2O react whenever, or formed whenever 1 mole of O2 reacts. So you use these coefficients in front of whatever it is that you're dealing with. to convert between things. So we've gotten out of molecules of water and into moles of water, and from there into moles of O2, and finally we can go from moles of O2 into grams of O2. Recall 1 mole of O2. All right, does 1 mole of O2 have a mass of 16.00 like you'll find for oxygen in the periodic table, or perhaps more likely 32.00? Yes, we're dealing with O2. You have to consider both 16s there. And so we've now set it up so that molecules ultimately is gotten rid of, and the only unit left should be grams. So let's go ahead and plug into our calculators 3.01 times 10 to the 23 times 32.00 divided by 6.02 divided by 10 to the 20 divided by 2. You should find that you get 8.00 grams of O2. That's how many grams of O2 were required to form that much water. If you didn't get that number when plugging into this calculator, it's probably because you were not using parentheses. I think that the easiest way of solving problems like this is to take all of those guys on the top, multiply them by each other, pressing enter constantly between each function, and then dividing by each of our denominators, pressing enter between each function. So I do this times that, enter, times that, enter, divided by 6.02, enter, divided by 10 to the 23, enter, divided by 2, enter. And so that should give you 8.00 grams of O2. All right, let's move on to another problem. The question is, let's see, how many grams of water should you be able to form if you react 14.34 liters of O2 gas, which are at 0 degrees Celsius and at 1 atmosphere, and presuming that H2, the other reactant, is in excess. So find the number of grams of water that should be produced, your theoretical yield, if 14.34 liters of O2 at standard temperature and pressure react with an excess of H2. Okay, so you want to go ahead and let me actually pull up our chart here. Our chart, let's see, gallery. Okay, chemistry. Okay, so here's a really useful chart in solving this problem. You'll see that we are told the initial amount of volume of O2 at STP, standard temperature and pressure. And we want to find the number of grams of that product. And so what we want to do is go from volume at STP, convert into moles, using the fact that at standard temperature and pressure, 1 mole of a gas has 22.4 liters of volume. So we'll go into moles of our O2, and then into moles of water, and then finally into grams of water. And so let's go ahead and get started on that. We have, let's see, 14.34 liters of O2. And for every liters to O2 to moles of O2, for every 1 mole of O2, 22.4 liters of that gas are present, but only for a gas and only at standard temperature and pressure for a gas. Okay, and so we can go into moles of O2, and from there we can go into moles of water. Let's see, our balanced chemical equation, you'll recall, had 1 mole of O2 for every 2 moles of H2O produced. And then we can convert from moles of H2O into grams of H2O. Let's see, I know that the molar mass of water is 18.02. Should I put an 18.02 here and a 1 gram here? No, don't do that. Instead, what you need to make sure of is that you are putting For every 1 mole of water, there's 18.02 grams of water. This is the definition of molar mass, the mass of 1 mole of this compound. Okay, so we've set this up correctly. Let's make sure we have our units canceling out. Liters of O2 should cancel, moles of O2 should cancel, moles of H2O should cancel, and the only unit left should be those grams of water. Okay, so in your calculator, plug in 14.34 times 2 times 18.02 divided by 22.4. And so you should get 23.07 grams of water. This is your theoretical yield, which is the amount of product that you should form given that all of your limiting reagent, i.e. not excess reagent, is used up, presuming that there's a full reaction of that limiting reagent. All right, which we'll talk about in our next video. I'll go ahead and draw a nice sunrise over a valley. Okay, thank you. Bye.